Inverse Laplace transfer function. So inverse Laplace transfer function, essentially, what we're trying to do is to separate or decouple your transfer function into the combination of two types, first order and second order. Once we know the first order and second order combinations, we should be able to identify what is the inverse Laplace transform based on the table. The homework is going to be talking about those kind of stuff. So let's work on one example. In this specific example, we are given So before we move on, there is one other thing I would like to talk about. So we know that if we have a system, sorry, this is not the example yet. So if we have our system, we got our G of S. On both sides, this is my input. This is my output. So essentially, what we're trying to do is output over input is going to be G of S. This part over here, you can use many methods to come up with the answer. If you know how to solve your homework, it's just basically the representation of equation of motions. So if you know the differential equations, you should be able to identify what's going on over here, right? If you do not know the equation of motion, for instance, you try to model a car, a vehicle. So this car has engine, has thousands of components in the system, but when you start to drive, I'm asking you to derive the equation of motion. Do you think it's feasible or it's possible? Probably not, because if you want to get the equation of motion, you need to identify thousands of components and put everything all together. Sometimes it can be very, very difficult, and it is going to be a lot of time. So instead of doing that, we would use sine wave on one side and get the response on the other side, so that we know the output divided by input. That is still our transfer function. This is more mathematically. We call this method system identification. Essentially, we will record the output in a sequence or a polynomial, and the output as a polynomial, the input as another polynomial. Output over input, we should be able to identify what's going on as our transfer function. So if we identify our transfer function, then the other thing is, okay, so I got many different kinds of inputs. How is my system going to respond to the specific input? That is another thing we need to know. So with that said, when we are dealing with output, we use final value, or sometimes we just call it FBT. I think we talked about this. You guys learned this in engineering mathematics already. So when we are dealing with something like this, we are trying to find the final value of output. It is going to be G of S multiplied by input. Right? Nothing fancy. It's just my transfer function multiplied by my input. The input over here can be few things if it's impulse. So delta of S, delta of T, then it's going to be 1. If it's unit step, or it's a 1, then it is going to be 1 over S. If it's going to be sine wave, Z is going to be S squared plus omega squared and S over here. Those are the things. You guys know that already in engineering mathematics, right? So when we have those kind of things over here, this one is periodical, so it won't achieve a steady state, which means if you give this thing a sine wave, it's going to be vibrating. When it's vibrating, it will never achieve a specific goal or the final value. However, if it's an impulse, like you got a cantilever, you put a hammer, what happened? It will start to vibrate. Then it will go to 0. If you have a weight over here and you hold it, if you release this one, what happened? It will start to vibrate, and eventually it's going to be something like this, right? It doesn't matter. This one is going to be similar to my unit step input. This one over here is going to be similar to my impulse input. So depending on which kind of input you're going to have, both of them are going to get to a steady state. When we are having a steady state, can you estimate how much this value is going to be? We can do that because we can use final value theorem. So final value theorem is simple. It is going to be, of course, I need to have my G of S multiplied by my R of S, right? This is my input. And when we try to find out the final value, what we're going to do is multiply everything by S and keep S close to 0. This is going to be my final value. Okay? So if you try to find what, just like the other two examples I just showed you, one is step input. If you have step input, you can certainly find out how much deviation the cantilever is going to look like using this specific formula. If it's going to be impulse, then you put a hammer in, it starts to vibrate, and when it reaches to its steady state, whether it's going to go to 0 or it's actually not going to go to 0, based on your final value theorem, you should be able to do the calculation. Okay, this is just one of the applications of the mathematical function you learn in Laplace transform. Any questions? You guys learned this in sophomore already, right? Let's do one example. So we are given a mechanical system. The transfer function of this specific system is G of S equals to 36 S squared plus 36 S cubic plus 4S squared plus 5S plus 20. So if the system is excited by a step input, determine the final output of this system. So pretty simple, right? Because I know this is my plane or my mechanical system. What is my goal? I try to find my output. And I would like to know what's my input. In this problem, I'm given unit input. And my G of S. What I try to find is final output. Pretty straightforward, right? It's just an application of final value theorem. So we can just apply final value theorem. So based on this specific configuration over here, this is my plan. Which one I'm looking for? This one, right? What is my input? Unit step input. So which one I'm looking at? 1 over S. So, and we need to use final value 0 because we're trying to find our final output. So, let's start from something like this. We are having S squared plus 36, S cubic plus 4S squared plus 5S plus 20. What do I need to multiply? R of S. That is going to be 1 over S. Is this the n? No. What do I need to have? S. So, cancel out the S. Replace S with 0. So it's going to be 36 over 20. So eventually, it will stabilize at 1.8. Does it make sense? Is that clear? Question? Should be pretty straightforward. Okay. If you do not have any question, let's work on another example. This specific example, the system dynamics of a mechanical system can be described by we want to determine the transfer function of the system and the steady state value of a step input to this specific mechanical system. And assume the input f of t is 0, but we do have initial conditions x0 equals to 1, x dot 0 equals to 4.27. We want to determine the time response or inverse Laplace transform of this output. So this is essentially something you need to do in your homework similarly. Okay, so we are given mechanical system. We need to find a transfer function and steady state response of u of t equals to 1 of t. Second, x naught equals to 1, x dot naught equals to 4.27. We need to find time response. Okay, should be pretty straightforward. This is just using inverse Laplace transform. Any question about what we're going to do? Nope. Okay. So let's start to solve. This is just an application of Laplace transform. So if I'm asking you to find out the transfer function, it means that I do not consider initial condition. When we are discussing transfer function, normally we do not care about initial condition. Why? Because the transfer function over here is the relationship between output and input, right? When we have initial condition, it's not really responding to its transfer function because it means that when you start your system, you are not having it stop. Instead, you are having it as some kind of initial position and initial velocity. What's the condition like this? Do you guys play this kind of card? And there is a like spring inside. So if you move this card backwards and release that, it will move forward with some speed, right? You guys have this kind of toy before?
Yes.
Okay, so if you do not move this one backwards, you just put it on the ground, will it start to move forward and backward? No, but if you push that, it will certainly moving at a certain speed because your hand is the input, which is the force. When you apply a force to this one, it will move forward for a certain amount of time, but because there are friction, there is a damping, there are spring, so it will move forward with certain speed and distance, then it will stop, right? But if you move it backwards, and you also put a force to this one, what happened? The initial velocity is going to be faster than the first example I showed you, right? So that is going to be your initial condition. With initial conditions, the system is going to have different response, but the response is not because the transfer function is different. It is because you are putting the system at different location. So when you start to release, you need to consider all those kind of initial conditions. It will going to give you some kind of different final value. Okay? Everybody understand what I'm talking about? Kind of? Let's do one. So, since we do not worry about the initial conditions over here, then we just apply Laplace transform to this thing. When we apply Laplace transform, this is second derivative, which means we're going to have s squared. One derivative is going to be s. Second derivative is going to be s squared. So over here, we are having phi s squared x of s plus 16 s x of s plus 80 x of s equals to 3.67 f of s. So we're going to have something like this. What is my output and what is my input? In this case, my output is going to be the position, my input is going to be the force. So it is going to be x of s over f of s. Therefore, I got 3.67 over here. I got phi s squared plus 16s plus 80. Any questions so far? Pretty straightforward, right? This one is something you learn in engineering mathematics, alright? Now, what we're trying to do is, this is the first answer you need to give me because this is transfer function. Second answer you will need to give me is what is a steady state result. So what kind of input I have? So my output is going to be multiplied by what? Unit input. 1 over s. I'm talking about steady state. So which zero I should use? Final value 0. So we can apply final value theorem. What do I need to do? I need to use limit as close to 0. And the other thing I need to have over here is what? As multiplied by everything. So cancel all this thing. S is 0. So essentially, I'm going to have 3.67 divided by 80, or the final value is that it will be stable at this is my answer. And this is my answer too. Any questions? Okay, that is my part of A. What is part of B? This time, I do not have any input. The input is going to be 0. So this part is going to be 0. But instead, I'm going to have initial conditions, which means my x0 and x dot 0, they are not zeros. So we need to use a formula that includes those two conditions when I'm doing my calculation, and we need to come up with what is the final value and the time response. So when we're doing something like this, we need to consider initial conditions. So it is going to be 5 s squared x of s minus s x naught minus x dot. Any question? This is the formula, so you need to s multiplied by x naught minus x dot naught. This is for the second order system. If you have higher order systems, then the formula is, you can find the formulas in your textbook or in your engineering mathematics textbook. Okay, this is for the second order. We have first order and zero order, so we're going to have 16 x of s minus x naught plus 80 x of s. So if you do a little bit calculation on this side, eventually we are going to have this is 1, this is 4.27. So if you combine everything all together and put to the other side, it is going to be 5s plus 37.31. Any question? Which means, in this case, we are not dealing with transfer function because we no longer have input. The input is, in this case, is what? 0. Whenever I put it. Then my x of s is going to be 5s plus 37.35 s squared plus 80. Okay. Should be pretty straightforward, right? Now, if we want to find the time response, we can use inverse Laplace transform for this one directly, which is going to be like this. However, this is a second order system. Sometimes it can be a little bit tedious for us to find out all the coefficients. So instead of doing that, we would like to have this part over here to be what? S squared plus omega squared, which will make everything easier for us. But since we have something over here, we do have S term over here. So what we're going to do is to make it like this. In the denominator, we would like to have something like this. Does that make sense to everybody? So this part over here becomes what? Square. This one is going to be my omega squared. On the other side over here, it is going to be phi s plus 1.6 plus 29.35. I'm not doing anything special. If you expand this one, it's going to be the same as this number. But why do I want to do this one? It is because if you put this one away, this part is what? Sine. If you block this side, what do you get on the other side? Cosine. So if you do the inverse Laplace transform, you can know it is going to be a combination of two terms. One is sine, the other one is cosine. We got s plus 1.6, it means that it's going to be delayed, or exponential negative 1.6t. That's something you guys can find out in your Laplace transform table. But you will need to separate that into this format. If you have a second order system, that will make the calculation a whole lot easier. Does that make sense? Okay, so if we do something like that, we are actually dealing with this. So when you are dividing, you are doing the inverse Laplace transform, you're dealing with this one and this one. This one is a constant or coefficient, you just take it out of the inverse Laplace transform sign. So when we do this one, this part is going to be sine. But I got exponential term over here because it's s plus 1.6, which means I should have this one in front of it. For the second part over here, I'll have 1.6 because this is 1.6. This one over here is what? cosine but again this one got s plus 1.6 over here, which is going to be something like this. Any question? Question. This one is going to be infinite, which means the s over here is going to be infinite, so this part over here is going to be what? 0, right? And this part 1 or 0. So this one is going to give us a steady state. This part over here is going to be giving us a steady state. So you can put t equals to infinite, and this one is going to be a constant, this one is going to be a constant, which both of those calculations is going to be 0. So you can find everything in this way. However, if we really want to find out what's going on over here without doing the inverse Laplace transform, what can we do? Final value theorem. So we're going to use two questions. Do I need to multiply this part by 1 over s? Yes? Or no? Or I don't even know what you're talking about. The question is, okay, is this one my transfer function? Yes, this is transfer function. No, this is system response. Come on, give me some.
System response.
Yes, this one is system response. This one over here is not transfer function. When this one is response already, you do not need to put an input because the input is 0. We talked about that earlier. So this is based on the initial conditions, what the response your system is going to look like. Does that make sense? So over here, since this one is system response already, we do not put 1 over s or 1, whatever you have on the other side. Over here, I write it down earlier. We do not use this over here. Make sense? However, the second question, I still miss something. What is the term I miss over here? S. It doesn't matter what you do. Final value theorem. You always need to have s in front of it. This time, my s equals to 0. So what eventually I'm going to have? 0. This is 0, this is 0, this is 0, so this is 37.35 over 80. However, we multiply by something which is pretty small, which is close to 0. So the output is going to be 0. This one is going to give you the same result as time approaches to infinite. So those two supposedly going to be identical. Does it make sense? So it doesn't matter if you use Laplace transform or you use time response, you should get the same result. However, obviously, Laplace transform is going to give us easier result when we are doing the calculation. If we try to find out time response, it's going to be a lot of calculation you need to do. That's the reason we do not prefer to use time sequence. Instead, we would prefer to use Laplace transform or transfer function to find out our response. Does it make sense? Calculation-wise, this is way simpler than this one. Any question? If you don't, then I have. By observing this one and this one, which parts are similar? Which parts are similar? Numerator or denominator? Numerator means 分子, denominator means 分母. Which part is similar? Denominator. This one is the same as this one, right? Why? Because the characteristic of in front of x components, they are identical. right? This is something we call equation. Which means your system characteristics is going to be the same. It has nothing to do with your inputs. Every time you have your system who responds like this, you got similar stuff. One is damping ratio, the other one is natural frequency. We talk about this when we are dealing with, we're going to talk about this when we are dealing with second order system. But for a second order system, we always need to worry about damping and natural frequency. It doesn't matter what kind of output you have from the external excitation. The system always has the same damping, has the same natural frequency. It won't change. Like you have your car, you have your bike. When when you ride on the road, if you ride at a certain speed, it's going to be wobbling and it's going to be vibrating. It doesn't matter whether you ride your bike on the bridge or on the road, or uphill, downhill. As long as they are the same speed, you're going to have the same natural frequency. It will be the same. It doesn't matter what you do. Your system characteristic is always the same. Does it make sense? Okay. That is. Now we're going to talk about more things about system transfer function. Okay, we got our transfer function, and we have numerator and denominator, right? Just like what we have on the other side. And you're going to find, we say that it's going to be either first order or second order equations, because we know since we are doing high school, memorize all those kind of formula. Even though I don't think it makes sense. I don't remember most of them, but it's going to be a combination of first order or second order. So we can always find out something like this. It's a multiplication. Okay, so you can always separate your numerator into a combination of multiplication of individual first order systems like this. You can do the same thing for your denominator. C over here is called 0. P over here is Paul. Okay, so the 0 over here is not number 0. It's just representing this is one of my roots in my numerator part. Paul is the roots in my denominator part. Okay, K is going to be transfer function. Sometimes those things are defined in your textbook. When we are analyze the system, there are a few things you need to know. First, n must be smaller or equal to n. Must. If your m is greater than n, system is not implementable. You're going to learn this thing in the future because what is s? Right? So if you have higher order in the numerator, you are estimating the future. For the technology we have nowadays as human beings, we cannot estimate the future. So if you try to build something, you have higher order in the numerator than the denominator. This thing is physically not implementable. Make sense? Mathematically, yes, you can do that. MATLAB won't tell you any error, but physically, you cannot do that because if you happen to find out something, you can see the future. Tell me, don't tell anybody. I'll hire you as my graduate students, and you're going to be my slave. It's a joke. So this is one thing you need to know. Second thing is denominator holds denominator dominates system response. OK， 我用中文讲一下。你在看圈数方程的时候，它会分成3个部分。第一个部分叫做 pole， 就是它你的分母的根。因为我们之前有讲过，所有的分或者多项式都可以被一次方程式或二次方程式组合起来。二次方程式最糟的情况就是它是虚数根，所以简单来讲，所有的denominator分母项全部都可以被一次方程式取代。这个东西叫做几点的，中文叫我不是很确定中文叫什么，这种叫0点。那0点和极点代表系统的站态、稳态和站态。这个分母一般来讲表示系统的动态方程。这个0点一般来讲系统的站态 （transient response） 会怎么动？它是不是会跑太过或是怎么样？那是 transient response 在这个地方表现。但是系统稳定不稳定，不是靠这边来看，而是靠这边来看。另外，分母的项值一定要比分子还要来得多，因为刚刚有讲过 ，S 是一个微分项。你如果这边的微分项高于这边的话，表示你可以预测未来。数学上来讲，这可以成立；物理上来讲，你无法看到未来。所以，如果你的项是这边比这边多的话，你的系统应该是不存在的。至少在人类的历史中，还不出现能够预测未来的东西。就算有预测未来的东西，它也不会让你知道，人家拿去赚钱就好了。所以 m 一定要比 n 还要来得小。如果你 m 比 n 来得小的话，如果你刚好发现 m 比 n 大的话，这个帮他讲笑话，你不要去告诉别人，你来找我，我会送你当研究生，然后你当我2年的努力，我再把它出专利，然后1毛钱都不给你。另外一个就是，如果你有极点的话，你的系统的动态会被极点所主导，0点只是站态的一些暂时的变化，所以如果你要讨论系统是否稳定，一般来讲我们是看你的分母，而不是看你的分子。所以在你分析一个系统的圈数方程的时候，你要注意的是它的分母，而不是分子。分子也重要，但是它相对来讲没有分母来的重要。有没有问题 ？OK， 我们休息10分钟。